Hello and welcome to Dr. T Math. In this video, I am going to give some examples of combinations, permutations, factorials, combinatorics, and we're going to start off with the counting principle. In a lot of cases, we can just count. Like, for example, a kennel has 7 cages. One dog can be placed in each kennel, each cage. How many possible arrangements are there for the dogs? And there's more than one way to do a lot of math problems. In this case, let's start by just thinking about the situation. We got 1, 2, 3, 4, 5, 6, 7 cages. We got 7 dogs, and so how many different dogs are available to be placed in that first cage? Well, we're starting with 7 dogs, and so there are 7 possibles that can be put in that first cage. Then let's move on to the second cage. How many possibles are available for that second cage? Well, we took 1 dog and put it in the first cage. Now there are 6 available. In the third, we're just going to keep on descending by 1. There are 1 fewer possible options for each next cage. And then by the time we get to the last cage, there's only 1 available. And then the little bit of math that we have to do, 7 factorial. Factorial means that we are multiplying all of the integers up to the number of possible things, or in this case dogs, we have to choose from. And you can omit the 1, but it's good practice to go ahead and write that down. Now we can do this by hand. 7 times 6 is 42. 42 times 5 is going to give us 10 and 200, or 210. 210 times 4 is going to give us 40 and 800, or 840. 840 times 3 is going to give us 120 and 2400, or 2520. And finally, 2520 times 2 is going to give us 5,040. But of course, that's why we have calculators. Here on the TI-84, we're in the math category, the math button, and then over in the probability, prob, P-R-O-B, part there, and I'm just going to put 7 factorial is indeed 5,040. And so there are, can you believe it, 7 cages, there are 5,040 possible arrangements for 7 dogs. They tend to grow rather quickly. Next example, we've got a true-false test with 15 questions. How many possible ways can a test taker answer all 15 questions? Well, let's just think about, for each question, there are 2 possibles. And this is very much like if we were flipping coins, we get heads, tails. There are 2 possibles for each. Each is independent. Each is independent, meaning that the outcome of the previous trial does not affect the outcome of the next trial. And so we can have true, false on any question, and we're going to get that 15 times. And so if you recall from other areas of probability, when we have these independent trials and we're trying to figure out how many possible outcomes there are, we're going to take the number of possible outcomes for each trial, and then we're going to raise that to the number of trials. And so if we kept on drawing this tree diagram, it would get rather big rather quickly. There would be a lot of leaves on the trees, a lot of branches on the trees. But taking it out just a few places helps us to see that if we just count 1, 2, 3, 4, 5, 6, 7, 8, we can confirm that is 2 cubed. And so if there are 15 questions and 2 possible questions for each, then that's 2 to the 15th. And we can again do this by hand. We're starting with 2, and then 4, and then 8, then 16, and then 32, and then 64, and then 128, and then 256, and 512, 10, 24, 20, 48, and we're getting up into the bigger numbers now, which is where the math gets a little bit more difficult to keep in mind to do just automatically. But if you are a computer person, then you should recognize a lot of these numbers. Base 2 is how we look at bytes and kilobytes and megabytes, and anything in binary, of course, is base 2, so you might recognize some of these numbers. 40, 96, the next one's going to be just less than 4100 times 2, which is 8200. 8200 minus 8 is 8192. Getting up into some pretty high numbers here, which is going to increase the chance of error. Let's look at 8200 times 2. 82 times 2 is 164, and we're going to be 8 less than 16,400 times 2. 8 less times 2 is 16 less than 16,400. So we're going to be at 16,384. And one more time, let's see if I can handle this computation mentally. 16,384, I'm going to round up to 16,400 times 2 is 32,800. 32,800 minus 32, that's double this one here. 32,800 minus 32 is 32,768, and I'm definitely going to go ahead and check on the calculator. 2 to the 15th power. 2 raised to the 15th power. 32,768. Got it. Okay, so there are 32,768 possible distinct ways that a test taker could answer a 15-question test. And notice that this is growing exponentially. We're not just adding more possibilities, we're multiplying by 2 each time, and so it grows rather quickly. In only 15 questions, there are so many possible ways that students could answer, which is kind of how teachers guess if students have copied off one another, because the number of combinations of potential answers on a multiple choice test are just so great that it's very unlikely that students would answer in the same way over all of many questions. Okay? Continuing on with this counting principle, let's look at a different way, a different type of question. A sandwich shop offers 5 kinds of bread, 4 kinds of meat, 10 different vegetables. How many unique sandwiches are possible if a customer selects one of each bread? So for bread, we got 1, 2, 3, 4, 5. And then for each of those 5 breads, we're going to have 1, 2, 3, 4 different kinds of meat, and then for each of those kinds of meat, they're going to get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And you can see again that the tree diagram gets really big really quickly. But the main idea here is that for each of the 5 kinds of bread, they're going to have 4 kinds of meat, and then they're also going to have 10 possible options for vegetables if they're choosing only one each. 5 times 4 is 20. 20 times 10 is 200. So there are 200 possible arrangements. And that kind of makes sense. If we just looked at how many possible options are there going to be out here, there are going to be 10 for this one, and then that 10 is going to be multiplied by 1, 2, 3, 4. So for each of these, like if it's white bread or wheat bread, for bread type number 1 and meat type number 1, we're going to have 10 possible. For bread type number 1, then we're just going to get rid of that. We're going to multiply it by 4 because we got 4 meat types for each bread type. And then we're going to be left with 4 times 10 for that first bread type, which is 40. We got 5 bread types, and so 40 times 5 is 200. And again, we could just draw out the tree diagram. It would be a big piece of paper. It would get really messy, and then we could count all of the distinct outcomes at the very right side of that tree diagram. Or fast forward 5 times 4 times 10 equals 200. How about, though, if a customer gets 2 vegetables? And this is more common. It's rare that a customer will only be allowed to get 1 vegetable. Usually there's multiple allowances there. Well, we know that there's still 1 kind of bread and 1 kind of meat. So we're going to be left with 20. And then we're going to have to do something like, if we've got 10 possible vegetable options, how many vegetables can the person choose the first time? 10, and then 9, and then 8, and then 7, and then 6. Possible choices as they go along. Does order matter? Is lettuce and tomato different than tomato and lettuce? No, order doesn't matter. If order doesn't matter, then we're going to have fewer possible options. And so what we're going to do here is apply a combination. That's n factorial divided by r factorial and n minus r factorial, where n is our big number, the total number possible, and r is our small number, the number we're choosing. So we're going to get 2 factorial and 8 factorial here. And we can do this by hand. 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 2 times 1 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. We don't need to write all those out. Actually, we know that we're going to get rid of that because of that. 10 factorial is really 10 times 9 times 8 factorial, and so we can just automatically exclude those. And then get rid of doubles here, change that to a 5. 5 times 9 gives us 45 possible options, but let's go to the calculator. And we are going to say, back to the math here, we're taken from 10, we're choosing 2, and we get 45. But remember, that's just the number of possible vegetable combinations, the number of ways that we can choose 2 vegetables from 10, and then we still need to multiply that by 20. So 20 times 45, 20 times 4 is 40, is going to be 800, plus 20 times 5 is 100, 800 plus 100 is 900, double check, 45 times 20, indeed 900. Combinations and permutations. If the order matters, then we're going to have NPR, which is n factorial divided by n minus r factorial. If the order doesn't matter, we're going to have NCR, or choose NCR, and that's sometimes NR vertically like that, which is n factorial divided by r factorial n minus r factorial. And you can see, because we have more in the denominator here for combinations, if lettuce and tomatoes is the same thing as tomatoes and lettuce, then order doesn't matter. And so the larger denominator, more in the denominator, means a smaller number. And so we'll have fewer possible outcomes. Let's look at another example. Decide if order matters or order doesn't matter. A sports club has 25 members. They want to form a committee of 5 representatives who will handle club scheduling, finances, and other business activities. How many different committees can be created? Well, if we choose, we've got every Tom, Dick, Harry, Michelle, Margaret, and Amy are in there. And is John, Maggie, Phyllis, and Mark, and Terry different from, so is this order, does it matter which way we group these people? Is Mark, Terry, Maggie, John, Phyllis different from Maggie, Terry, Mark, John, Phyllis? No, so order does not matter. That means we're going to be doing 25, choose 5. Order does not matter. If we're choosing 5, that means we got 25 factorial divided by 5 factorial, and then 20 minus 5 is 20 factorial. So let's say 25 times 24 times 23 times 22 times 21 times 20 factorial divided by 5 times 4 times 3 times 2 times 1 times 20 factorial. We're going to get rid of our 20 factorials there, and now let's look at some common factors. 5 goes into 25 5 times. 4 goes into 24 6 times. 3 goes into 21 7 times. And 2 goes into 22 11 times. So what we're left with is 5 times 6 times 23 times 11 times 7. And we could go through and do this. Sorry about that. We can go through and do this by hand, but it is faster if we just go into a calculator. Most scientific calculators will have this here. 25 choose 5 gives us 53,130 possibles. And let's just do 5 times 6 is 30. 5 times 6 is 30. So we got 30 times 11 is 330. 330 times 7 is going to give us 2100 and 210s. 2100 and 210 is going to be 2310. And then we got to multiply that by 23, and that's where it really gets messy. 5 times 6 times 23 times 11 times 7. 5 times 6 times 23 times 11 times 7. 53,130, so same outcome. Next example, there are 27 boys in a track meet. How many ways can they win gold, silver, and bronze if all 27 boys compete in the event? Well, gold, silver, bronze order matters. If person A gets gold and person B gets silver and person C gets bronze, that's different than if person B gets gold and person C gets silver and person A gets bronze. All right, so since order matters, we're looking at NPR. That's 27 permutation, choosing 3. And that's going to be a lot more possibilities, a bigger number, and so doing it by hand is just impractical. So we're going to go 27, 27, go to the math, and PR, 27, taking 3 out of there, 17,550. 17,550. Same thing, there are 32 girls at the track meet. How many ways can they get gold, silver, bronze? Order still matters, so we got 32P3 because depending on who wins gold, silver, and bronze, those are distinct outcomes. 32P3, 29,760. 29,760. And finally, if the boys and girls are on the podiums together, how many different ways can there be both boys and girls winning gold, silver, bronze up on there? Well, we're going to take 32P3 and we're going to multiply that. So each of the possible combinations, each of the possible arrangements of the boys or of the girls can be paired with each of the possible arrangements of the boys. And so we're just going to multiply these together. And we're going to get 20, let's go back here, 29,760 times 17,550. And that's equal to 522 million, what was it, 788,000? 288,000. 288,000 possible arrangements of 3 boys and 3 girls out of only a total of 59 boys and girls. And so that's quite a lot. That's a huge number. And that is combinatorics, counting and multiplying. It's really not difficult operations. There's nothing really elegant about it, or there's nothing really complex about it. It is kind of elegant. But it really is just multiplying and adding, figuring out how many choices are available, and then maybe a little bit of using a calculator from there on out. This has been Dr. T's Math. Thank you.